morning, everyone. It's been a nice weekend. Anyway, your exams are getting graded, so that's you'll hear right away once they're done. I'll just post everything in Gradescope and homes and so on. But it might need a little bit of time. It's going well. We'll see. Anyway, we are. We'll continue. Last time, the last thing we started mentioning was we're going to talk a little bit about rational and irrational numbers and give a couple irrationality proofs using some things we learned. So just a reminder, if you could write a number r in the form a over b, where a, b are integers, and of course b should not be 0 in this expression, then r is called rational. So rational numbers are quotients of two integers, and we'll do some things today. We'll prove certain things are irrational. Anyway, just some notation, which is just extremely common in mathematics. That I don't know if we'll actually be using it a ton, but you're welcome to. It's just the following symbols. So when people write z like this is the set of all integers. When people write q with a similar sort of style like that, this is the set of all rationals. And of course, I'm sure you've seen this before. This is the set of all reals, set of all real numbers. Okay, and then we'll be talking about irrational numbers. These are real numbers that are not rational. So in terms of set notation, that's represented by this. This is supposed to mean you take the set of all real numbers and then take away all the elements that are in this set. And so what remains are just the irrationals. So that's just a way to describe the set of irrational numbers. All right. So anyway, we'll be working with rationals, and there's one important thing you can always do when you have a rational number, which is something you're familiar with, an old concept, which is you can essentially have your fraction be reduced as much as possible. And let's explain that in terms of our language. So anyway, here's an assertion. So if you have a rational number, r, then the point is you could always do the following thing. So you could always, first of all, you could write r as a quotient of two integers. That's just what it means to be rational, but we could assume something extra. So this can always be done in such a way that the GCD of the numerator and denominator is 1. Okay, so the numerator and denominator share no factors in common. And of course, you know what you would do if they did, right? If they shared a factor in common, you could just cancel that factor off, and then they don't share it in common anymore. So this is always possible. This is what you'd probably call a reduced fraction. And it'll actually be very important for us today. We'll want to assume things are in this form at some point. But anyway, this is a really straightforward proof. It's supposed to be an extremely straightforward idea that you're all 100% on board with. But let me just explain really quickly what we already did that makes this a quick proof, which is that, given any, so not with this assumption of GCD AB equals 1, but given any, say, R equals A over B, with the GCD of A and B equal to something that perhaps is not 1, what you can do is you can take R, which is A over B, and you can write it as A divided by D divided by B divided by D, like that. So that's the same quotient. D divides into A and B because it's their GCD, so those are actually integers on top and bottom. And on top of it, there was a thing we proved a while back that if you take a pair of integers and divide each of them by their GCD, you get relatively prime things. So the point is then GCD of A over D with B over D is in fact 1. things that did not satisfy this condition, you could divide out by the GCD and now they do. Okay, so that's just why you could always assume it's always possible to be in that form. Okay, so anyway, what we're going to do here is prove a couple things are irrational. So the first one we're going to take a look at is kind of the first, I think as far as I'm aware, it's historically the first thing that was proved to be irrational, I think. I think there's a big controversy, in fact. But square root of 2 is irrational. I heard some story once, I don't know if it's true, so I'll repeat it for you. But something about, I think it was maybe Pythagoras and his people back in the day figured this out, and then it was a big controversy because everyone thought every number was a ratio of integers, and then they were sworn to secrecy and they didn't tell anybody. I don't know if that's true. Anyway, but, what's that? Is that a real thing? Yeah. Well, the two of us have heard it.
Someone got killed, I think.
Yeah, maybe.
Multiple people got killed. Yeah.
Oh, okay. So I mean, I see this is like someone told me 25 years ago, and now I'm just repeating whatever I remember. But yeah, it's.
Beings had souls.
What's that?
They also thought beings had souls.
Well, who knows, right? Anyway, so this is. Anyway, we'll give a nice quick proof of this. But as we just said, though, it goes back a long ways, and I'm not so sure that anyone proved anything was irrational before this. But anyway, the story is then like, well, why? We have to prove it. So for a proof like this, I mean, a proof by contradiction is a good way to get started because it gives you something to work with. So you could say, well, let's suppose it's rational. So suppose for a contradiction, it's rational. Okay, and the point is that gives you something to work with because you get to assume that it has the form A over B. And we're going to also do this thing, right, where we're going to assume that it's kind of in reduced form where A and B are relatively prime. So this would mean that somewhere out there we could write the square root of 2 as, there are two integers out there, so the root 2 is A over B, where A, B are integers. And of course, we'll assume this extra thing because we're allowed to, that they are relatively prime. Okay. And so what we're going to do with this then is the only thing we can do, which is you have to use the fact that you're working with the number square root of 2, which has a certain specific property that makes it special, which is that its square is 2. Right? So you can square both sides of the equation. So if you square both sides of the equation, you get that the number 2 is a squared over b squared. Okay, and this is good because it's really an equation about integers. And in fact, you can make it even better. This would imply that 2b squared is a squared. Right, so now this is really an equation about integers. No division or anything. And we just have to figure out what's wrong with it. Okay, so look, the thing is that the left-hand side is even, right? It's a multiple of 2. So the right-hand side is even as well. Or what we could say is just that 2 is a divisor. So what happens is this shows 2 is a divisor of a squared. Or really just a squared is even. Okay, now this was going to imply that a is even, but I mean, if you establish some basic facts about evens and odds, you could say that, but we could just do one better and say, this is a prime that divides a product of 2 numbers, so therefore this prime must divide one of the 2 factors, right? So since 2 is prime, it follows that 2 divides a. Right? You could say 2 divides A or 2 divides A, but therefore 2 divides A. So A is even. That means we can do the following. We can write A as 2 times C for some C. All right, and then then what we can do with that is put that back into our equation with a and b over there. Okay, so what we have is that 2b squared is a squared, which we just said a is 2c. Okay, so a squared is 2c quantity squared, that's 4c squared. So you have 2b squared is 4c squared. And then you could divide both sides of this equation by 2 to get this. Okay, and what you have now is that b squared is 2 times something. So this is telling us b squared is clearly even as well. Okay, so similar to the steps above, we could say this shows that 2 divides b squared, just like we had before, and then similarly follows that 2 divides b. Okay, now what's the problem, by the way? This is supposed to be practically the end of the proof. So you know what the problem is? Yeah.
Both A and B are even.
Right, well, what's the problem with that? I guess.
It's not fully simplified.
Right. So this is why this was important now, so this thing over here. So we assume they're relatively prime. So they cannot both be divisible by 2, because that contradicts the fact that they're relatively prime. Okay, so what we've shown is that 2 is a common divisor of A and B, that's our contradiction. This contradicts the fact that we assume GCD of A and B is 1. Okay, so now we have a problem. Okay, no, it's not a problem actually, it's the end. It's good. But that's the end of our proof. Okay, so if just viewed a different way, if we didn't never assume this in the first place, what would happen is if it's rational, they're both even, so you could divide them both by 2 and replace them with a different fraction, which again would still be the square root of 2, and then it would still both be even, and you'd have this sort of paradoxical infinite descent thing where you could keep dividing the numerator and denominator by 2 forever and ever. It doesn't make sense. It cannot be. Okay, so that's sort of the standard proof of square root of 2 being irrational. We'll kind of generalize this to other numbers. I mean, you could put other numbers there and try the same kind of proof. But we'll try to make a stronger statement in a moment, not just about square roots, but other roots as well. Okay, so proof okay? All right, you try this proof, like I said, for other numbers, like 3 or something, you'll go through this exactly the same. If you try for 4, it's not going to work, right? Because 4 is, the square root of 4 is in fact rational, right? So it's not just that the square root of anything is irrational. So there are some numbers whose square roots are rational, like 4 and 9, for example. Okay, so we're going to try to say something really general. Of course, for those numbers, their square roots are rational precisely because they were perfect squares in the first place. Okay, here's a very general statement about kth roots of integers. So this is theorem 5.3. So suppose k is this is going to be an exponent for us, something that's at least 2. Or exponent slash root. So then suppose we have a positive integer. What we're going to assume is that this positive integer is not a kth power of another integer. Okay, and so the statement is that the kth root of n is going to be irrational in this case. So, I mean, what this is sort of saying, by the way, is that, if if n were a kth power of an integer, then when you try to evaluate this, you get that integer, right? So one of two things is going to happen for an n is that when you take the kth root of n, it's either going to work out to be an integer or it's irrational. Right? But that's all that can happen. Yeah.
Just out of curiosity, would there be a much simpler proof that if you have 2b squared equals a squared, there's got to, from unique factorization, you have an odd number of factors of 2 on the left-hand side and an even on the...
Exactly, yeah. Well, yeah, we could have done it that way. I mean,
Okay.
yeah, in fact, that's what we're going to do in this proof.
Okay.
Because it'll work a little nicer. In fact, this chapter was called something to the effect of applications of unique factorization, which we didn't actually use in that last proof. We'll use it here, though.
So is that why you did this construction, is to get around using unique factorization?
Well, I mean, I just did it, I think, because it's simpler. I mean, there's no reason to get around it now, because
I've proven it.
we proved it, so we can use it. But I think this is a really classic proof. It's just so it's nice to share, I think. But in fact, if you really get into it, I mean, you could argue we use this fact about when P divides a product, then it must divide one of the two factors. But it's really simple. We just did it for 2. Like you could prove this on like day 1 of this course that you know, if something like if a square is even, then the thing you've got with square is even. Like it's really much lower level. But anyway, now that we're trying to say something pretty general, we'll appeal to unique factorization. But anyway, your point is exactly correct, though. You could argue a different way that if you look at prime factorizations, the number of 2's that could possibly be on the right would have to be a multiple of 2. And on the left, you're going to have an odd number of factors of 2. So it is contradictory there. So that's going to be the argument here. It's just not about evens or odds or something, because we have kth powers. So let's take a look. So this one, the proof. Right, so this statement is filled with some very negative sounding assertions, like something is not this, and being irrational is also a not condition, right? Saying it's not rational. So this lends itself towards a proof by contraposition. So we'll prove the contrapositive statement, which is equivalent to the original statement. So that would be the statement that if the conclusion is false, then the assumption is false. So we'll say, we'll assume this is rational, and then prove it's a kth power of an integer. Okay, so let's assume the kth root of n, we'll write it as a over b, is rational. And so we'll show n is a kth power. That's meant to, I mean, I wrote it more carefully, but I mean kth power of an integer. Okay, so we'll use unique factorization here. So let's, okay, so if a kth root of n is a over b, then by definition of kth root, you could raise both sides to the kth power to get that n is a to the k over b to the k. Okay, so what we have is that n b to the k is equal to a to the k. Okay, and so let's just bring some factorizations in. So let's write, well, we'll write them like we were writing, I think last time or the time before, where we were writing things like 2 to an exponent times 3 to an exponent times 5 to an exponent, etc. Like that. Where the understanding is every single prime is written there, but all but find how many of the exponents are 0. So let's do the same for b. Okay, and so what happens then is that we have this equation that says nb to the k equals a to the k. And if we look at the left-hand side of this thing and we look at all the the primes and group them all together, what we have is, on the left, is for all the 2's, we have an n2 showing up once. But if b is raised to the k power, then you get k times b2. And when you multiply the powers of 2 together, they get added. So you have this as the exponent. And so this is what happens for every single prime. So you have 3 to the n3 plus k times b3. 5 to the n5 plus k times b5. For all the primes. Okay, and this is supposed to be a perfect kth power of an integer. Okay, and so there was a thing that we mentioned last class. I think it was last class at some point that we said that if you have a kth power of an integer, then all of its prime exponents have to be multiples of k. Okay, so the prime exponents of the kth power are multiples of k. Okay, so what that means then is that all of these exponents are divisible by k. So k divides, I guess, n sub p plus k times b sub p, for any prime p. Okay, but look, this k times bp is already a multiple of k, so that's going to imply the np is a multiple of k as well. Okay, so we'll exercise if you need to work it through carefully, but this implies this can only happen, right, if this term is also a multiple of k, because that one's a multiple of k. So k is going to divide np. You should prove that, so you're not getting any kind of wrong ideas about why that conclusion is following. But anyway, this implies k divides np. And so that would be true for all the p's, which means that every one of the prime exponents of this number n is a multiple of k. So that's what we wanted. Right? So this implies n is a kth power. And so we had some result that we are appealing to here, which we mentioned that a number is a kth power if and only if all of its prime exponents are divisible by k. And we're using it in 2 different directions. Right, so here we're saying it is a kth power. This thing is a kth power, so its prime exponents are multiples of k. But now we're saying the prime exponents of n are multiples of k, therefore it's a kth power. So we use essentially both directions of that if and only if statement until it is proved. Okay, but anyway, this gives you loads of examples of irrational numbers then. Okay, so I mean, we had square root of 2, we could have lots of other square roots, we could have lots of cube roots and fourth roots and fifth roots or whatever you want to write down. We could just scribble a couple examples down. Okay, not anything, but many things. So, cube root of 9, fifth root of 8, examples. These are irrational. I wrote something like this. It's not. That's 2. Okay, that's the only way out, right? If this thing simplifies to be an integer, then of course it's not irrational. But if it doesn't simplify to be an integer, our theorem is saying it's irrational. One common occurrence, I guess, is you could have the kth root of p is irrational. Let's say for any prime p. And integer k that's at least 2. Right? So that's already an enormous family of examples of irrational things. Okay. All right, so anyway, this theorem sort of supersedes the last one, I guess, right, in that you could use this theorem to imply the square root of 2 is irrational too, if you like. Okay. All right, so, okay, question? Yes?
Do you mind being a little more explicit as to why k divides n?
equation says it's a Kate power, right? I mean, so we did have a theorem. We didn't prove it, but I'll explain it real quick. But I mean, we said that when a number is a Kate power of an integer, then all of its prime exponents have to be multiples of K. I mean, the point is because we didn't write a prime factorization explicitly, but if we did, you'd have a thing like this, right? Okay, and I mean, what we are actually using, if you take a careful look, is the full power of the fundamental theorem of arithmetic, which says not only do you have prime factorizations, but they are unique, which means if you have an equality of two prime factorizations, you get to conclude the exponents are the same, and all the exponents over here are multiples of k, which means all the exponents over there are multiples of k. Right? But that is, in fact, using the uniqueness of the fundamental theorem of arithmetic. Anything else before we talk about the next thing? We're going to keep talking about rational and irrational things, but what we're going to actually take a look at is what's called the rational root theorem. State and prove in a second. Okay. You guys know the rational root theorem? Rational roots of polynomials? I'm wondering if they teach you in high school. No? You know what? Well, maybe wait till I tell you what it says. I don't know. I'm trying to remember if I learned it in high school, but it's too long ago. Okay. Anyway, if you never learned it, it's a good time to learn it now. So it's about roots of polynomials and being able to basically find the ones which are rational if they exist. So, of course, polynomials, the roots of polynomials need not be rational numbers, but sometimes they do have rational roots. So this is theorem 5.4, which is called the rational root theorem. And it goes like this. So we're going to have a polynomial, just totally. Well, first of all, it'll look pretty generic, but we are going to assume something. So we have a polynomial of x. So a thing that looks like this. Okay, what we're going to assume about the coefficients of this polynomial is that they are integers. Okay, so this is going to be a polynomial with integer coefficients. What we're going to assume about this thing is that an is non-zero and a naught is non-zero. So two comments about this. First of all, the assumption that an is non-zero is an extremely natural assumption, right? Because if an were equal to 0, that would be like this term's not even there. And this is supposed to be your top term of your polynomial. And so if it's not really there, then this is really your new an. And so that's really natural. The assumption that a naught is non-zero is, I'm trying to figure out if we really need to make that assumption. But if a naught were actually 0, the thing that can be done with this polynomial, if this is gone, is you could factor out an x now. And then you take an x out, and then the other factor will have the property that this is non-zero. Or if this were 0, you could factor out an additional x. So you could essentially always get yourself into a position where you're talking about this case. So it's kind of harmless assumptions. But we are, what's more significant is we assume we have integer coefficients. And anyway, so we didn't get to the theorem statement yet. It's about what possible rational roots could exist. And so the assumption is that we have a rational root of this polynomial. So if r equals u over v, if this is a reduced rational number, so I mean, that's fractions reduced, so the GCD of u and v is 1. But if this is a reduced rational number, which is a root of p, so that means with the property that if you plug it into the polynomial, you get 0. Okay, a polynomial like this should have no more than n roots, and so if we say we have a rational one, the conclusion is going to be that we get some divisibility for u and v. So u is going to divide a naught, and v is going to divide a. All right, so that is the statement of the rational root theorem. So what it's, we'll apply it just to show you like a little later after we prove it, to explain how it often gets used. But I'll just kind of say it out loud first, which is this. You know, that if you were searching for roots of this thing, and specifically we're looking for rational roots of this polynomial, what this is telling you is that there's not a lot of options for what they could be. So, you know, you have an actual integer here and some actual integer there, which only have so many divisors, right? So there's only so many candidates for what u could be, and there's only so many candidates for what v could be, which means there's only so many candidates for what u over v could be. Like there would be a finite number of possibilities. And so if you were searching for rational roots, you could actually, you know, consider the finite number of possible roots, rational roots, and then, you know, maybe brute force check your way through them to see which ones give you 0 when you plug in. And if there are rational roots, you can find them that way. So that's one way this can be used. Okay, so there are plenty of examples where there's, you know, an extremely limited set of divisors of a n and a naught, and then you can, you know, say something non-trivial. Okay, so anyway, let's prove this first, and then we'll talk about using it. So, all right. So anyway, starting point is this. So since this is true, right? So we're assuming we have a rational root, so that when you plug it into p, you get 0. So we just want to actually plug it into p and set it to be 0. And so we get. Right, so let me just plug that in for x. So we have a sub n u over v to the n, right, plus a n minus 1 u over v to the n minus 1, etc., down to a1 u over v plus a naught. So that equals 0. Okay, now what we're going to do to this equation is clear out all the denominators. So, I mean, this is number theory. We like working with integers, not so much rational numbers. Anytime you have stuff with rational numbers like this, you could almost always convert the equation into an integer equation. So what you would do here is just try to clear out all the denominators at once. So multiply both sides of the equation by v to the nth power to get rid of them all. So if you were to do that, you would have a sub n, just u to the n here. And then we'll multiply this by v to the n, and what happens is you cancel one of the v's you multiply by. So we have u to the n minus 1, but there will be an extra v. Okay, so what this is going to look like, I'll write one more term, even though it wasn't here. It was here somewhere. But this is to the n minus 1. So you would have that many u's, but when you multiply it by v to the n, you're left with 2 v's. So you'll have a pattern developing that looks like this. Here, when you multiply this by v to the n, you have just v to the n minus 1 comes out. And then this last one has no v's on it. So what it looks like across the board here is if you add up the exponents that you have for the u and the v in a term, they should add up to n. But that's what it looks like. And notably, this is important, notably, there is a term here with no v's, right? And then there is a term over here with no u's, right? But everything else in the middle is a mixture of v's and u's. So let me, let's call this for this equation as star, because we'll manipulate it twice. Okay, so first thing we can do is, so rearranging So I'm going to rearrange it, I guess, in two different ways, but we'll do one at a time. So for the first one, let's isolate this term. Okay, so let's isolate that term, which means move all the other terms to the opposite side of the equation. So we're going to, I guess, keep this one here, move everything else to the left. Okay, and where this is going to end is with that A1 term. So A1 u v to the n minus 1, right? So what's happening here is that in this right-hand side of this equation, what you can see is there's always at least one u in every term, okay? So this thing right here, this is divisible on u. Each term has at least one u. Right? You could actually factor out a u from all those terms. Okay, n. I mean, n is at least one, by the way. Okay, anyway. So probably could have said that. No one wants to talk about constant polynomials anyway. Okay, so here we go. So this is divisible by u, so what that means, I mean, because this equals this, right? Here's where you get somewhere. So u divides a naught b to the n. Okay, that's a non-trivial conclusion, right? And but then what we're trying to prove is something else, which is that we're actually trying to prove that u divides a naught. Right? And so this has this annoying v to the n attached to it. Okay. Now there was a thing that was assumed here in the statement, right? Is that u over v is supposed to be reduced, which means we were actually assuming the GCD is 1. Okay. So anyway, the argument then is that since the GCD of u and v is 1, we're supposed to get our conclusion, but let's be a little careful. What follows from this is that, first of all, the GCD of u with v to the n is also 1. Okay, that could be a little exercise if you need to check it out, but it is in fact true. If u and v have no factors in common, then u and v to the n will also have no factors in common. So a small exercise. But then where we have ourselves is we know u divides a product. Think of it as a product of two things. But the GCD of u with the second factor is 1. So it's supposed to follow that u divides a naught. And that's an old thing we proved in the past. Okay, so it follows. And so you need to remind yourself exactly what it is that says this is okay. Here's the reference. But u divides a product of two things, and it's relatively prime to one of the factors. And so therefore it follows that u divides the other factor. Okay? So that's why we get that u divides a naught. And then we still have to do the other thing. But it's a similar argument. Let's just give it. Okay, are we okay with this argument? We're about to give a similar argument, but what we can do now is going back to this equation we had. We're going to play a similar game. We're just going to rearrange it a different way, where we're going to leave this term on one side and move everything else to the other. So rearranging star in a different way. All right, so you can leave the an u to the n alone, move everything to the right. Right, what does this look like? So this is on the left, move everything else to the right. So this goes down to a1u v to the n minus 1 minus a naught v to the n. Right, and so we isolated the only term that had no v's attached to it. And so the right-hand side, everything is divisible by v. So this is, like everything has a common factor of v. So what we get is that v divides this left-hand side. Okay, now we're about to give a very similar argument to what we gave right here. Okay, so since we do know GCD of u to the n with v is 1, what we get is what we want, which is that v divides an. So, So, I guess what's true, just going back to something I was talking about before we proved anything, is I guess the argument, like we never used the fact that a naught or an is non-zero. It's just if one of them was 0, this is a useless conclusion, right? To learn that an integer divides 0 tells you nothing. Everything divides 0. So if you weren't working in the case where something was 0, you don't get any information. And the bigger picture point of that is that you can always put yourself in the case where they're non-zero, and then you get information. So it's more about if you want to get useful information, you should make sure those hypotheses are satisfying. Okay. So anyway, that's the rational root theorem. Let me show you how we use it. Okay. So we'll do something practical. Do you guys have questions on this proof? It's not a terrible proof, but so here's an actual problem. So what we'll do is use the fact that the following polynomial, so p of x is 2x cubed plus x squared minus 9. We're going to use the fact that this has a rational root. We're going to take advantage of that fact and find all of its roots. Okay, which may in fact include some complex numbers. But so we have some information which is not something that would have to be true for a cubic polynomial. Not every cubic polynomial would have a rational root, but this one happens to have one. Okay. Now, it also has 2 other roots which turn out to not be rational, but we're still going to find them all. We're going to find all the roots, but this is going to be a very useful piece of information. So anyway, if we know that this thing has a rational root, then by the rational root theorem, we learn something. We learn some divisibility statements. So if R equals U over V is a rational root, right, then by the rational root theorem, what we learn is that U has to divide the constant term coefficient, so -9. Okay, and V, the denominator, has to divide the top coefficient. Sorry, V divides 2. Okay, so where this lands you is that there are not so many possibilities for U and V. Right? They are integers and they divide these numbers. So Divisors can always be negative, so you have to account for that. But what's going on here is, u could be plus or minus 1, could be plus or minus 3, or it could be plus or minus 9. But those are the only integer divisors of -9. And likewise, v could be plus or minus 1, or it could be plus or minus 2. Okay, so you get yourself in a position where you could actually just look at all the possibilities, and there's not that many. That's maybe more than you'd want to, well, not that many, we'll see. So the possible numbers you can get by taking one of these u's divided by one of those v's, these are all the potential roots. So the possible roots are, well, you could have, just consider every combination, but you could have plus or minus 1 divided by a plus or minus 1, which will give you a plus or minus 1. Or you could have plus or minus 3 over a plus or minus 1. Or you could have plus or minus 9 over a plus or minus 1. But you can also have any of those u's divided by like a plus or minus 2. Okay, and so that means you could also have 1/2, plus or minus 1/2. You know, plus or minus 3 halves, and you could have plus or minus 9 halves. Okay, and so, that's 12 numbers, which is a very finite amount of work. And what you can do, which is a little tedious, admittedly, if you're going to do it by hand, but it can be done, is you can just check them all and see which one's a root, right? So you could just try them all. Okay, and so I won't actually do it all, but what eventually you would find is it turns out it's 3 halves. Okay, so it turns out that when you try this one, what happens is you get 2 times the cube of this number plus the square of this number, minus 9, and if you sort out what that is, then you'll, it's supposed to be 0. Okay, and so you can check that. But now, where that tells you 3 halves is the root. Okay, so when you find it, though, the point is that, okay, the fact about polynomials is if you have a number that's a root, that means that x minus the root is a factor of p. So x minus 3 halves is a factor of p of x. So it should be possible to factor that out. By the way, this also implies, because if you multiply this by 2, you get 2x minus 3. So that's also a factor. Okay, and so where you would go just to finish this, so now we're just about pushing it here with time. But what you can do with this information is you can take p of x. And this is telling us that we could factor out a 2x minus 3, and we'll have something else left over. Okay, and so you can take your time and carefully figure out what quadratic would go here. I'll just tell you what goes here, because we're out of time. But once you know you can factor this out, you can actually do polynomial division to find the quotient, which is the other thing. And then once you have this factorization, and you say, I want to find all the roots, the last step would just be you can use the quadratic formula to find the roots of this. Okay, that thing has 2 roots, and those are your other 2 roots. And so they turn out to be complex numbers, but you could actually find them. And that's how you can take advantage of this theorem to actually factor this polynomial, find all 3 of its roots.